Work and energy, they're measured the same way in units we'll talk about in a second called joules. Work is the transfer of energy from one system to another. So on the left, we got a system has a certain amount of energy in it. In the right, we've got another system has a certain amount of energy in it. And we're going to say those are currently closed systems. In other words, the energy doesn't leak out or whatever. Well, work is when we transfer energy from one of the systems to another one of the systems. And the one loses energy and the other one gains energy. And the energy is conserved in the process. And what we do for work is we say system 1 does positive work on system 2. Think of system 1 as you. Think of system 2 as a cart. When you push a cart, you give it kinetic energy, which we'll talk about. And so you've increased its energy, but you burned some calories. So you lost some energy. So energy was transferred from system 1U to the cart. We also say system 2 does negative work on system 1. We could say the cart took energy out of your system is a way of thinking of it. So system 2 doing negative work, it's harder to look at it there than let's look at it the other way. Let's pretend the first one was the cart and the second one is you. When if the cart's rolling along and you slow it down, then you've taken energy out of that system. It's a little harder to see when we talk about people where that energy goes, but the energy was transferred out of the cart. So in other words, system 2, you did negative work on system 1. And the equation that we have for AP Physics C is work is the integral of F dot dr. Dr is a little small displacement vector. Okay, very small displacement vector. And that dot in the middle is the dot product. And so what we end up doing is we're taking the magnitude of F, the magnitude of dr, and that dot product is the cosine of the angle in between them. And we're adding up all the little contributions because R doesn't have to be a straight line. It can be this curved line. So we're going to take all these little tiny, for an infinitesimal element of work, it's the force on the object times the displacement of the object times the cosine of the angle in between. So here's an example of what we're looking at. If you're pushing an object, I don't have the object drawn, but you see it pushing along that path, then when it moves a little tiny bit in that direction dr, then the work ends up being F dot dr, force dr times the cosine of theta. And work ends up being a scalar. So it's not a vector. We take vectors to figure it out, but it can be plus or minus. Unit is joules. If you think of force, kilogram meters per second squared, dr displacement is going to be in meters, so you end up with kilogram meters squared per second squared. It's really useful to know that joules is a compound unit that's made of kilogram meters squared per second squared. Dot product. And that's what I'm talking about with the dot product. The magnitude of F times the magnitude of dr times the cosine of the angle in between. And we add all those little contributions up. So if this thing in the upper right was going to be, if you use this force to move it along that path, think of a bead on a wire or something like that, where it can only slide along that path. But we apply a horizontal force. To figure out the total work done by that force, we'd have to go for all the little drs that make up that path, and we'd have to figure out F times the length of that little infinitesimal displacement times the cosine of the angle in between. Now, the good news is, very frequently, the force is constant and the motion is along one direction. In other words, not this curvy path. So the simpler version of this is Fr cosine theta, force times the distance times the cosine of the angle in between those two vectors. Really important, because you're going to have situations where there are all sorts of angles going on. We might have an inclined plane, as we'll see soon. The theta in this equation is the angle between the force vector and the r vector. And I call this theta confusion. Sometimes you'll have problems where it's a ramp and theta is given as the ramp angle. Here the theta is the angle between those two vectors. So I always think of this as Fr cosine of angle between. I'll write BW an awful lot. that saves a whole lot of theta confusion. So I'll just write it as A dot B is AB cosine of the angle between BW. So what we're going to do now is we're going to look at work done by each force in this problem. And again, I've done the free body diagram for you, but it's very easy. mg, everything else is a contact force. Normal and force of friction are the surface forces. Tension is pulling up at this angle theta. See, there's that theta again. So it moves a distance d to the right at constant speed. Okay, well, if it's moving at constant speed, we know it's in equilibrium. That's really important. And we want to find the work done by each force. And then we want to find the total work. Well, let's look at gravity first. Gravity is down, always down. But this thing is moving to the right. So the angle in between mg and the distance factor is going to be is going to be 90. So you have mg, fd cosine theta. These are all, we don't have to do this integral because it's one direction for the displacement and one direction for the force. So mg times d, force times the distance, times the cosine of the angle between. Notice it's not that theta that's shown in the diagram. It's the angle between those vectors, which is 90 degrees. So we have the work done by mg is 0 joules. If we do the work done by tension, the force is T, the distance or the displacement is D, and so it's T, D, cosine of the angle in between them. That happens to be the theta that's shown in the picture. Okay. Normal force is also perpendicular to D. So ND cosine of 90 is 0 joules. So gravity and the normal force do no work on this. We'll see why when we get to the work energy theorem. Or I should say, we'll see why that makes sense. And then finally, friction. Well, this one, if you think of it's moving at a constant speed, then if T cosine theta is pulling to the right, then it must be T cosine theta pulling back to the left if it's at a constant speed. Ordinarily, if it wasn't constant speed, we'd have to do mu, normal force, right? That will give you the force of friction, times d, times the cosine of the angle in between, which is 180. But here, we don't even have to solve for normal force to find this because we know it's in equilibrium. The constant speed makes this a little easier. So we know the force backward is T cosine theta. So we have T cosine theta times d times the cosine of 180 because that's the difference in angle. That's the angle between d, which is moving to the right, and friction, which is moving to the left. So it's negative TD cosine theta. Now, I want you to notice another thing. Let's go back up to the work done by the tension. Another thing we could have done is we could have broken that into two components. We could have had T cosine theta to the right, T sine theta up. Okay, and this is going to be a little trickier. The force up, just like the normal force, is perpendicular to the motion. There's no work. The sine of the angle in between T sine theta and D is 90 degrees. So it ends up being 0. And then T cosine theta is pulling in the direction of the motion. So you'd actually have T cosine theta times D times the cosine of 0 degrees, which is 1. So you end up with that same result whether you break it down into components first and do two forces, or you treat tension as just that one force. Okay, so let's see that total work. Well, total work is 0. 0 joules mg, 0 joules normal. Work done by tension is Td cosine theta. Work done by friction is negative Td cosine theta. So basically what's happening is as fast as you're putting energy into the system, friction is taking that energy out of the system. Here's a little tougher problem. We're on an inclined plane. The angle of the ramp is 40 degrees. We've got the mass. We've got mu k. It slides 8 meters down the ramp. We find the individual works and the total work. Work done by mg. Now it's not 0 because it's not perpendicular to the displacement down the ramp. Okay, so we have mg is 350 times 8, that's the d, and then the cosine, it's a little tricky here. The cosine of the angle between those two vectors is 90 minus 40, it's 50 degrees. okay, because you have a right triangle there. If the ramp angle is 40 degrees, the angle between those two vectors ends up being the complement of that, which is 50 degrees. So the work done by mg is 1763 joules. Gravity is putting energy into the system by making it go faster down the ramp. Work done by the normal force, normal is perpendicular to the surface. That's going to be at an angle of 90 degrees, so there's no work done by the normal force. Friction. No, we actually have to calculate the friction. Mu times the normal force times d times the cosine of 180. Remember, friction pushes up the ramp. D is down the ramp. The angle between those is 180. So the angle between. Notice I didn't use 40 degrees really for any of these arguments for the dot product. But the normal force is going to be, as we knew, mg cosine of the ramp angle, mg cosine 40. So we have mu mg cosine 40 times d times -1 ends up being -630 joules. So my total work, 1133 joules when we add all those together. Once again, gravity is putting energy into the system. That's what's moving the thing down the ramp. Friction is taking energy out of the system at the same time. So the total work, the total change of energy of that block ends up being 1133. And I mentioned we can break down vectors, we can not break down vectors. If we break down vectors, we could do this. Excuse me, before we had 350 times 8 times cosine of 50 is 1763. We can do that slightly differently here. It looks like I went off the side there, but we could break it into components. Okay, so the component down the ramp is 350 sine of the ramp angle, 350 sine 40, times 8, the displacement, times the cosine of 0, because the component of mg down the ramp is in the same direction as the displacement. Then we take that perpendicular one, 350 cosine 40, times 8 times cosine of 90, because the component into the ramp is perpendicular to the displacement down the ramp. So that first term will have some value. The second term will be 0. And guess what? Sine of 40 is the same as cosine of 50. We end up with the exact same number. Or we could take all the forces, add them together to get the net force, and then do that with the dot product of D. And guess what? Perpendicular to the ramp, those cancel out. Along the ramp, we have mg sine theta pulling down the ramp minus mu mg cosine theta times d times the cosine of the angle in between, and we'll end up with the same total that we had before. So there are other things we can do here. I want to show you that there's multiple things. So now, that angle is 150 degrees shown there, and we want to find the work done by the force over the 5-meter path. Well, we can break this up into chunks. The first chunk, they're in the same direction. So FD, 10 times 2, times the cosine of 0 degrees. And then the second chunk is going to be 10 times 3 times the cosine of, there's actually a 30-degree angle between the force and that 3-meter vector. So when we do that, we end up with 45.98 joules. Now let's talk about calculus. Once again, calculus, we've got to use all the different work elements. So we always write this as work equals integral of f dot dr. But we could really write it as work is the integral of all the little tiny work elements. Because in that last one, we had 2 work elements. Well, now we want to add this up, and we want to get these together, f dot dr. So let's take an example here. We got a force on the right of 5x. So as you go farther and farther to the right, the force is increasing. I really wish I had that as an arrow that's getting bigger. Force is to the right of 5x, and it travels a distance d. So what we want to do is add up all the little work elements. We can't just multiply 5xd, because we don't know what that x is, right? We've got to add all the little tiny chunks along the way. Okay, so the little dw at the beginning is going to be different from the dw towards the end, because it's going to be a bigger force towards the end. So we integrate f dot dr. The force is 5x. dr is going to be my dx, a little tiny chunk in the direction of the x vector. And that'll end up being 5x dx. And we're going to integrate from 0 to d, all the way out to the full distance d. And when you do that, you get integrating x dx is x squared over 2. So we have 5 as a constant that we factored out, times x squared over 2, evaluated from 0 to d, and you get 5d squared over 2 as your answer. 2.5d squared. Okay, find the work done by the force if the force is in the x direction. Okay, now here what we're doing, whenever you have this integral of f dot dx, it's the same as really saying the area under the fx curve. So that's the area of the under the fx curve. When you see a graph, sometimes look and say, okay, I've got on the y, I've got the f, on the x axis, I've got x. See if there's an equation that has those two things multiplied together. And if it does, and it's an integral, then you're probably good doing area under the curve. So what do we have? The first area is 4 times 6, the rectangle. The second area is 1/2 times base, 2 times 6. So we have a total of 30 joules. Ends up being really easy. Now, if we do it with calculus, we'd actually have to have two equations. We still have to break it into two parts. So let's do from 0 to 4, the force is 6. Okay, so from 0 to 4, we have 6 times dx. And we're assuming they're in the same direction in this. That's really kind of important, actually. So integral of 6 dx is 6x from 4 to 0. So we end up with 6 times 4 is 24, which we found in that previous one. Now, the equation for that line for the force in the second part, from 4 seconds to 6 seconds, is 18 minus 3x. When we integrate that, we're going to break that into two integrals, 18 dx and negative 3x dx. And when we integrate those, we have 18x minus 3x squared over 2. And lo and behold, we're ending up with the exact same energy, same work transferring energy. Let's find the work done by a spring. That's important. Not the work you're doing on the spring, but the work done by a spring as it extends from x1 to x2. Well, if it's starting at, let's just say that x1 is equilibrium, closer to equilibrium, it's stretching, it's expanding, the spring is going to be pulling back. So W equals F dot dr. The force is going to be kx. We know that. This is F equals kx for a spring. And so we have kx dx times the cosine of 180. Why? As we extend the spring by pulling it farther, its force is pulling back. So it's going to do negative work. We're doing positive work on the spring. Spring is doing negative work because it's pulling in the opposite direction of the displacement. So we have kx, the magnitude of the force, times dx, how far we're stretching it, times the cosine of the angle in between, which is 180. So that ends up being negative kx dx. That's negative k x squared over 2. And I've got that from, it should be from x1 to x2. Sorry about that. So it ends up being negative k x squared, x2 squared minus x1 squared over 2. We could also do that by doing the area under the curve. If we look at this, it's a shape, it's a quadrilateral. The area of that shape is going to be x2 minus x1 is going to be the base, and the height, we can do it by averaging kx1 and negative kx1 and negative kx2. So the area ends up being the exact same thing that we got in the previous example.